Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Southern California Gas Company, California Resources Corporation, Kern Schools Federal Credit Union, Panama Buena Vista Union School District, Bakersfield City School District, and the San Luis Obispo County Office of Education, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
And I'm Scott. We'd love to have you join our show today, and the way you do that is to give us a call. If you have a math problem you'd like us to solve, you can call us if you're here in Bakersfield. The number is 636-4357. If you're in San Luis Obispo, we'd love to give you a call, or have you give us a call as well. The number is toll-free. It's 866-636-6284. You can even email us a math question that you have, dothemath@kern.org. You can watch the show online, of course, dothemathonline.net, and if you have any type of social media, you can find us there as well. We are on Facebook, Instagram, Twitter, and YouTube.
We can call San Luis Obispo
them
County,
as well. Yeah.
right?
Yeah.
Perhaps make a reservation for a meal. You can bring us over and treat us for the afternoon.
That'd be kind of nice, as long as I get some Doc's ice cream at the end. That'd be
Yes,
nice.
that is indeed what's going to happen, because every time we go over and visit some schools, we always have a lovely meal, and then we top it off most often with Doc's. That's some good stuff right there. Speaking of good stuff, we've got a lot of good stuff planned for today.
We do, yeah.
We'll get to the food items in just a little bit. Right. But we do have phone tutors available until 5:30, as we do most Tuesdays and Wednesdays throughout the regular school year. We have a very special guest in studio. We'll go out and about with Marylou. But before we do any of that, let's first take a look at today's Math in the News. And today's Math in the News has to do with food.
Food, good deal.
Let's take a look at the board right there, and you know what that is?
Ice cream.
Yeah, it would be nice if it was ice cream, but it's not ice cream. It is indeed mayonnaise.
Mayonnaise, all
You a
right.
fan of the mayo?
I'm a big fan of the mayo, just not solo, right? You got to have it on something, and then, you know.
I can't imagine eating
not
just
by
a
the
spoonful of mayonnaise.
Not so much.
You know, and I would say I am a 99% non-fan of the mayo.
Okay.
I mean, there are some places that make some coleslaw or something, you know, and a little cup of maybe,
Got to make the sacrifice.
Puckett's macaroni sal's got a little, but other than that, keep the mayo out.
All right.
So I found a story, and let me read this to you first. So Michigan State University has more than 50,000 students enrolled at any given semester. And they have bulk food deliveries, as you can imagine, as any university would, distributed to the campus dining halls. In 2016, the university received 500 2.5-gallon tubs of mayonnaise.
All right.
Now, the student diners immediately noticed that something was not good with this.
Uh-oh.
All right. The mayo had frozen and then thawed.
Okay.
Okay, but they're still serving it.
Uh-oh.
Okay. Now, that's about 10,000 pounds of mayonnaise. So what they did is they turned it into electricity.
All right, now I'm really intrigued. How does
now,
this
right?
happen?
See, which is exactly why I, figured, all right, we need to do something with this and bring some math into it, all right? Luckily, in 2013, the school had opened up an anaerobic digester, a sealed tank deprived of oxygen in which organic waste is degraded at an elevated temperature, allowing certain types of waste material to decompose quickly and produce methane that can be captured and used as fuel.
Okay.
All right, so they had this already on campus.
Yeah.
All right, so let's fast forward to this photo right here. All right, so they've got 10,000 pounds of mayonnaise.
Yeah.
Now, mayonnaise is essentially egg yolks and cooking oil. Very high fat content.
Right.
All right, and a great meal for the bacteria in the digester to feed on.
Okay.
So they had 12 employees spend an entire day dumping container after container into this anaerobic digester to turn this into electricity. Can you just imagine the aroma?
I can only imagine. I don't even want to think about it
I
too
mean,
long.
just imagine the mayo rotten by itself.
Right.
And then you've got all of this other lovely stuff going in there. Spend an entire 8-hour day just dumping that.
Yeah.
And I'm sure some of it splatters.
Right. So do you have a hazmat suit or do you have a mayo suit on? That's the question.
So so it was a good thing that they had that, to be able to dispose of that 10,000 pounds of mayo.
Right.
So, all right, other than the number 10,000, how are we going to tie some math into this? Well, you need to know your pints, quarts, cups, gallons, and all those types of things.
There you go, okay.
So a lot of kids see these, in elementary school to learn all of the different measurements, and you know that you've got 2 cups in a pint, right?
Yep.
So you've got 2 pints in a quart, you've got 4 quarts in a gallon.
I like that picture, that's a good one.
So those are little things, and then a lot of times they're like, all right, well, make sure you mind your P's and Q's.
Oh,
That's
there
saying.
you go. All right.
And that saying was, make sure you mind your P's and Q's, knowing the difference between pints and quarts.
Okay, that
So
makes
if you're
sense.
delivering something, which should be a pint or a quart, you need to mind your P's and Q's.
All right.
And that is today's Math in the News. 636-4357 is the phone number. We do have phone tutors available until 5:30 this afternoon. We have a very special guest in studio. Dylan, how are you?
Good?
You ready to roll?
Yes.
All right. Why don't you let everybody know where you go to school and what grade you're in?
I'm in 5th grade and I go to Stockdale Elementary.
Home of the Stars, right? And how long have you been there?
6 years.
So you've been there since kindergarten.
Yep.
You like it pretty well?
Yeah.
It's all right, not too bad. Huh? If you could fix one thing at Stockdale, what would it be?
Nothing.
Soda in the drinking fountains. Isn't that what you said? Put soda in the drinking fountains. Wouldn't that be great?
That is true.
There we go. Okay, so at least we have some suggestion for the principal.
All right. Now, what soda would you put in?
Oh, there we go. Good question.
I'd probably put where you could push different buttons and they'd all be
now we have
the
selection.
suicide thing, right?
Yeah.
Put all the different things in there. All right.
right.
Well, you know what? Maybe you can have an opportunity. We'll send you to a restaurant. You can go make one of those. All right. 636-4357 is the phone number. We do have phone tutors available, and what we're going to do right now is we're going to go to the phones right now because we are going to get ready for our first phone call of the afternoon. Are you ready? We'll find out what the student is up to. All right. Karina, is this who's on the line? Hello, Karina.
Yes. Hi.
How are you today?
Good.
All right. As soon as you're ready, let's hear the math problem that you're working on.
Okay. Henry, Janet, and Clark are playing a card game. The object of the game is to finish with the most points. The scores at the end of the game are Henry with -7, Janet with 0, and Clark with -5. Who won the game? Who came in last place? Use a number line model and explain how you arrived at your answer.
Oh, wonderful. All right, Karina, did I hear you right? You said we're going to use a number line. Is that right?
Yes.
Okay, so I'll get a number line ready to go. And maybe you can tell me about what range we should have on our number line. In other words, what is the smallest number we should have on the number line, and what is the biggest number we should have on the number line?
You could have, it could go all the way from -10 and 10.
Oh, I like that. That's wonderful. Now, how'd you pick -10? That's a great choice, because it's not -7. We went all the way down to -10. Good choice. How'd you pick that?
Because I don't want to go too close to 7 because I might run out of room.
That's a good point.
Yeah.
Okay, so I'm currently making a number line. I'm going to run out of room here in a minute. But it's okay because we have a neat little eraser here, so we'll make our number line a little bit bigger. And you said you wanted to go all the way to +10?
Yes.
Okay, so that's going to be a pretty long one here. So I'm at -1 here, and I'm going to get a 0. Now, how did you choose +10 to be the ending point of your number line?
Well, my teacher always said we had to do the opposite
Okay,
of them too.
good choice. I'm not going to quite make it. I'm going to make it to 8, but on your paper, if you can make it to 10, that's probably a good choice. Okay, so we have a number line now created from -10 to +10. I'm a little bit short, but I think we're going to be okay there. And what's the next strategy that you would use to figure out where these numbers fall on the number line? You want to just put a dot there? Is that okay?
Yes.
Okay, sounds good. So what's the first one you want to put on the number line?
0.
0. Okay, that's a pretty easy one to find. And we'll just put a big old dot right there at 0. Now, which person in the game scored 0 points? What was the name there?
Janice.
Janice, okay. Okay, which one do you want to put on the number line next?
-5.
-5. Okay, I'm going to go over here to -5. I'll put a dot there. Which person in the game scored -5?
Clark.
Clark, okay. And we have one more score. What was the last score that we have to put on the number line?
-7.
-7, right. So I'm going to put a big old dot at -7. And who was that person?
Henry.
Henry, is that right?
Henry. Yes.
Okay. So I hope that you're following along here, either watching the show or making your own number line. But as soon as you can see the number line and see where everyone lands on the number line, you probably can answer those questions that you have. What was the first question that we need to answer in this problem?
Who won the game?
Who won the game? So from the number line, who has the highest score?
Janice.
That's it.
0.
Yeah, she's number 1. Go Janice, number 1 with 0 points. Doesn't happen very often, but apparently this is a game where 0 points will make you the winner. What's the next question you have?
Then who came in last place?
Who came in last place? All right, so who's last place on our number line?
Henry.
Henry, okay. Sorry, Henry, you got last, man. Any other questions we have to answer about this problem?
No, only just to use a number line model and explain how you arrived at your answer.
Ah, gotcha. So we have this number line. I'm going to ask you one more question. Are you ready for this? Janice was the winner of the game, right? Here's my question for you. How much did she win by? She beat Clark, right? Clark's in second place. How much did she win by?
7.
Oh, she beat Henry by 7. I agree with you there. But what about Clark? How much did she beat Clark by?
5.
5. There you go. And all you got to do is you can either count on that number line, just hop 2, 3, 4, 5, or you can do a little math as well. But that's right. Janice won by 5 points, so she had a little bit of leeway. But even with 0 points, apparently in the game they were playing, she is the winner. I'm glad you called in with that question. Thank you.
Nicely done, and congratulations, Karina, for a lovely call right there. We're going to send you a free pizza, courtesy of our friends at Cubby's, Chicago-style pizza, so congratulations on that. Hey, we do have phone tutors available until 5:30. We've got Dylan in studio, but right now we're going to go out and about with Marylou.
Wonder how speed limits are determined on a street or where signals are placed. Well, today we are at the Public Works Traffic Division and I'm with Ed Murphy, Civil Engineer 3. How are you doing?
Doing wonderful.
Can you quickly tell everybody exactly what it is that you do here?
We are in charge of pretty much all things traffic in the city. We have 2 divisions, one's in planning and development, and one's in operations. I'm in charge of operations. That's handling signal timing, striping on the roadways, everything that the cars are using while they're out there, cars, vehicles, bicycles and pedestrians out there on the roadway. And then there's the planning division, which develops future streets and future projects and things like that. So,
can you tell us where we are right now?
we are right now in our office here at City Hall in the Public Works Traffic Division. There's 8 of us on staff here, about half of us for operations, half of us for planning. And this is where all the magic happens as far as trying to keep traffic flowing efficiently and well throughout the city of Bakersfield.
Now, there's another room here in your office
There is.
that is really interesting.
It is.
And can you take us to that?
I would love to. It's called our Traffic Operations Center.
Okay.
Let's head back there now.
And what exactly is going on here in this room?
Well, the Traffic Operations Center is, we have programs in the computers that are connected to all of the city's signals. Well, I shouldn't say all of them, but at least we have about 420 signals, and at least like 380 are connected through the city, through conduit that we've been placing in the roadways on construction projects for the past 20 plus years. Anytime there's construction going on, we would lay this in the ground, and then we pull fiber or copper wire through and have it bring all those signals here to this brainchild, if you will, the Traffic Operations Center. And this is a map that shows all the signals that are connected to the city. Each one of these little dots is a signal light out there in the city, and if it's green, that means we have good communication from here all the way out to the signal light, wherever it is, out in the outskirts, or even close to downtown here. You can see all the signals that are really congested right down here
Now,
in downtown.
we were talking earlier about the different colors, and I was talking about getting here. I had to travel down Rosedale Highway.
Right.
So I was kind of wondering, hey, am I being detected on Rosedale Highway? What lights am I going through? And then you were pointing out the white. What does that mean with the white?
The white,
lights?
we don't have communication with it at all. The red shows that we have communication with the signal, but it means we've lost communication with the signal. That's not necessarily a bad thing. For example, here near the freeway, this is 99. These are Caltrans state signals, so although we have connection with it, we're not in control of it. That's why those stay red all the time. But other places, such as this on, I believe that's Ming Avenue, there may be something wrong with that signal out at Ming. If there is blue, that's another alarm that something's wrong with it, but the red means that we've lost communication. That could be a construction project that's going on. Not necessarily always a bad thing, but at least it warns us to let us know we don't have communication. If an emergency vehicle comes through, these lights turn pink. It shows that they're being preempted. You know, a fire truck or an ambulance or police, you know, needs to get through and clear the intersection. They have a little strobe light on top of their car that triggers this little thing that's on top of the signal light. And it reads it and it knows that an emergency vehicle needs to get through. And it turns the signal green so that they can make it through the intersection. Obviously, when someone's life is in danger, we want to get the emergency first responders there as fast as we can.
So you don't
and
have
this helps us do that.
the cross traffic.
You don't have to sit there waiting
Yeah.
for the light to change. It preempts it, it turns it green so the intersection can clear and hopefully prevent a
Over
disaster.
here, we got
Yes.
cameras going on.
Yes, these are connected to these. The cameras, we have about 30 cameras, not at every location, obviously. We have way more signals. We're adding more as time goes on. That's great. Here's an example of, we could see what's going on out there. We're not recording anything, but if there's something, a triggered light, let's say it goes red or something, we can pull up a camera if we have that in the location and see maybe there was a collision out there that took out the box, or there was something else that's happening for a flood or something, or maybe it looks like nothing happens and maybe that triggers that something's wrong with the wiring and the signal itself. But this gives us an idea of what's going on, behavior at the intersection. Here's something also that's reflecting the same intersection, Stockdale Highway and California Avenue. And these are both in real time. You could see the eastbound through and the eastbound left turn lanes, it has a green light right now. So as you saw them, they were turning left and going through still. Now it turned yellow, and one of the other directions is going to turn green. Right here, the through south and the through left, and there they go.
There they go.
And then they're making the left turn. So
Now,
that's
you
also
even can
fine.
see pedestrians, right?
There are. Here's a pedestrian right here. They hit the button, the pedestrian button. Unfortunately, we can't see them on the deal there. And they're wanting to cross this way, it looks like. So the signal knows when you press that pedestrian button, there's a pedestrian here, and it usually gives a little more time for a typical walking pace for somebody to make it across the signal, or to make it across the intersection. And Stein Road and Cal, it's a big intersection. It's not like a local road where you live in your neighborhood. It's, you know, wider. Typically about 90 feet or 110 feet usually about
Wow.
there.
Well, there's
So-
a lot of math required with this, right?
is.
So when we come back, we're going to kind of go over how you determine speed limits, correct?
We will see, yeah, how we can determine the speed of a car, yeah.
Awesome. Okay. And we will be back in a little bit.
All right, thanks for that, Marylou. Hey, we do have phone tutors available until 5:30. We'll go right back to the phones. And Audrey, how are you this afternoon?
Good.
And you're a 6th grade student, correct?
Yes.
All right, as soon as you're ready, let's hear the math problem that you're working on today.
Okay. If two rational numbers A and B are ordered such that A is less than B, then what must be true about the order for their opposites, negative A and negative B?
Oh, interesting. All right, that sounds good. So we want to be able to compare negative A and negative B. Wow, Audrey, I like this question a lot. Do you have any numbers at all to give us? Because all I hear is letters.
I used 1 and 2 for A and B.
Oh, so you put some numbers in there. That's a great strategy. I like that strategy a lot. So you chose some numbers so that A and B would work in the first part you told me? A is less than B, is that right?
Yes.
Okay, so which one did you put as 1 and which one did you put as 2?
A is 1 and B is 2.
Okay, that totally makes sense. So 1 is less than 2. There you go. So then it sounds like we need to compare the opposites, right?
Yes.
Okay, so what would negative A be?
Negative 1.
Negative 1. And what would negative B be?
Negative 2.
Negative 2. Now we're going to go compare those things. Do you think that we can compare them just by looking at them, or do you want to make a number line so we can see where they are?
I want to know if we can make a number line. So
That sounds
I can
good.
See where they
I
are.
like that. We did a number line in our last problem, and it seemed to help us out quite a bit. So I'm going to make a number line. Can you tell me the range that we're going to go on this number line? In other words, what is the lowest number that you want on the number line, and what is the highest number?
Negative 5 to 5.
That's a great choice. Any specific reason that you chose those numbers?
They're both, they're higher than negative 1 and negative 2.
Yep.
And my teacher told me that when we're doing a number line, we should use opposites.
I like that. That's great. So it sounds like that message is getting out loud and clear because we heard that from the last caller as well. So we have a number line from negative 5 to 5. And I think one of the best strategies is just to put some dots on the numbers where these points lie. So you told me at the beginning that A is less than B. I'm going to go ahead and put a dot at number 1, and we say this is A, and a dot at the number 2, and we say this is B, right?
Yes.
And you can see, hopefully on your number line there, that A is less than B because A comes before B on the number line. Now what happens when we go and put the opposites on, right? That's the part that we really want to know. So let's see if we can go down here and down to negative 1. We have this one here. This is negative A. And then we have a negative 2, negative B. So which one on the number line is bigger now? Remember that arrow has to continue to point the same way. So if I have the arrow going the same direction which it needs to be, it looks to me that from the number line, things have switched around, haven't they? The negative A is bigger than the negative B. In other words, negative 1 is bigger than negative 2 because it's further to the right on the number line. So can you repeat the last part of the question? I think there was some kind of conclusion we need to make here.
Then what must be true about the order for their opposites?
Ah, gotcha. So in this specific example, can you tell me what must be true? If A is less than B, what happens to negative A and negative B? Which one is bigger there?
Negative A is bigger than negative B.
That's right. Now, can you tell me what you might do, because we only tried one pair of numbers, right? What would you do with this problem just to maybe try another one? Or can you say that for every single number in the whole world?
I think so.
Yeah. It's a good question to ask yourself, isn't it? And it's a really kind of a fun mental exercise to have to say, does this really work for every number that we possibly have? So maybe what you want to do, this is a wonderful conclusion, at least in this specific example, maybe try 2 or 3 more on your own just to make sure that you come up with the same conclusion. If you start off with numbers and one of them is less than the other one, when you change the signs, the opposite of that happens. If you have opposites of the numbers, you have opposites of the greater than or less than sign. It's probably going to be true, but you might want to try a couple more.
Okay.
Okay? Good question. Thanks for
Fantastic
calling.
problem right there, Audrey. Wonderfully done. And because of that, we will be sending you to the movie of your choice at Maya Cinemas. So congratulations on that. Hey, we do have phone tutors available until 5:30. We're going to go to the phones in a couple of moments, but right now we need to get Dylan to work because you've been sitting here listening to a lot of kids do their problems. We need to make sure you can do some math today. You ready?
Yeah.
All right, head on over to the board. We're going to look at your homework assignment paper here. And it says to do a tape diagram, and we're going to go ahead and do that with the first part of your problem here, all right? When someone donated 14 gallons of paint to Rosendale Elementary School, the 5th grade decided to use it to paint murals. So we've got 14 gallons. They split the gallons equally among the 4 classes. So there are 4 classrooms that are going to use 4 gallons, or 14 gallons.
So there's 4 different classrooms we're going to divide that into, right?
So 4 classes.
4 classes. Gotcha. Okay.
So part A, how much paint did each class have to paint their mural? So let's figure that out first.
Any way you can do a tape diagram to get that one going for us? We got a lot of
I feel
lines
like this is
there.
going to take too long.
It is going to take a while. That's exactly right. Now think about this a little bit, right? Tell me a little bit about the tape diagram. What does the whole tape represent? Does it represent?
It represents the 14.
The 14, gotcha. So we got to have 14 things, right? And we're going to divide them into 4 different pieces. So you think you need a bigger tape?
Probably.
Okay, let's do that. Let's make a bigger, longer tape here. Okay?
So then,
And it comes up like that. There you go. Any idea how many lines you're going to have to make
13.
14 sections? 13. How'd you know that? Have you had some experience with this before?
yes.
It's always one less, isn't it? Okay, let's see if you can put 13 lines in there. Here we go. I think it's going to work this time. Good. 9, 10,
11.
11, 12, 13. All right, so we have this. Hey, we made it. That's exactly right. So here's a tape diagram. We have 14 sections because you got 13 lines. And what are you going to do with this 4 part?
Well, so let's see. 4. Oh, wait. 14. 4.
Oh, okay,
4
do
can
some
go into
dividing.
14
Okay,
3 times.
all right.
2.
Yeah,
So then it would have 2 left, but 4 can't go into 2.
right. Yeah, bad deal. So what do we do with that extra 2 there?
Remainder.
Okay, got a remainder. You want to put the remainder as an R, or do you want to make it as a fraction? Because we have this tape diagram, we still got to do something with the remainder, right? Okay.
I think I might want to put it as a fraction.
Okay. Yeah, it's kind of interesting.
Yeah.
Now, when we look at this tape diagram, what are you going to do with all those boxes? You're going to shade them in? You're going to
Yep.
cross them off?
Well, since we have 3 and remainder 2 left,
Uh-huh.
3.
So you got 3 of those strips there. There's
Yep.
3. And what about that remainder 2 part? Have you ever done that where you make a remainder into a fraction?
I've seen it before.
You've seen it before. Well, let's go ahead and do it then. If you've seen it before, at least it won't be brand new to you.
Yeah.
So I really like how you had that 2 left over. And that's exactly right. You got the 2. And we'll make it into a fraction. Any idea what would go on the bottom there?
Probably 4.
That's right, because you divided by 4. And I know you're a pretty smart guy, so before we do anything with the 2/4, how can you reduce 3 and 2/4?
You could simplify the fraction.
Okay, let's simplify it. What do you get? You need a little
1/2.
more room there?
1/2.
1/2. All right, so right down here, let's go ahead and, 1/2, and keep the 3 with it as well, okay?
Okay.
Keep the 3 out in front. Okay, so you filled in 3 of these here. How are you going to fill in a half? Show us on your tape diagram. How are you going to fill in a half of one?
Fill in half of the tape diagram.
There you go.
So
We'll do
7.
half of one right here, huh? There you go. Fill in that top part there. There you go. So we have 3 and a half. Now what do we do?
Hold on, let me think.
It's good thoughts, huh? Yeah, exactly. The theory, according to your math here, is that we should be able to have 4 equal parts just like that. So let's do a little Christmas thing here. Ready? You did one in red. I'm going to do one in green. Here's my half. 1, 2, 3, right? So we have one classroom that's going to get 3 and a half, and another classroom is going to get 3 and a half. Now you do another one.
And the other classroom's going to get 3 1/2.
Yeah. So you got half. 1, 2, 3. Let's see if there's 3 and a half left for that last classroom. 1, 2, 3. Where's the half? There it is right here. No, it's left over there. So we have 4 full classrooms that get 3 1/2 gallons apiece. I like your division, and we have a great picture that goes along with it. That's a good deal.
There you go. Nicely done, guys. We'll go ahead and continue on that problem in just a few moments. But because you've gotten off to a great start, we'll be sending Dylan to Chick-fil-A. Get yourself a nice meal over there. There you go. Everybody's having to get some Chick-fil-A. Hey, don't forget, we have phone tutors available until 5:30. We're going to go to the phones right now. And Brian, how are you this afternoon?
Good. You?
I'm wonderful myself. Are you in 7th or 8th grade?
7th grade.
All right. As soon as you're ready, let's hear that math problem.
Okay. Jasmine walks 3 miles each day. Write and solve an equation to find out how many days it would take for Jasmine to walk 75 miles.
Okay. Sounds good. So did I hear you correctly? You said she walks 3 miles each day. Is that right?
Mm-hmm.
Okay. So how do you want to attack this problem? At some point, we want to make it to 75 miles, right?
Yeah.
Gotcha. Any way that you want to specifically start this problem out?
I don't know really.
Yeah, there's all kinds of ways to do it, huh? Well, let's at least start from the beginning, right? If you walk 3 miles a day, right?
Yeah.
3 miles on Monday and 3 miles on Tuesday, Wednesday, Thursday, Friday. In 5 total days, how many miles would you go?
Okay, so 15 miles.
That's it. Yeah. So in 5 days, we would go 15 miles. So that's not going to quite work out so well.
No.
Because we'd have to do a whole lot of adding if we wanted to get all the way to 75.
Yep.
Well, let's take what we have here. We added up all these 3s and we had 15. So because we did 5 days, what is a way that we could end up, if we started with 15, like we have a total here,
Yeah.
and we have 3 miles a day, how do we get back to 5?
Subtracting.
15 and 3. You could do some subtracting, but you just use those numbers, 15 and 3. How could you get back to 5? What do you think? 15 times 5? No, that'd be too big. 15 minus 5 won't quite work out, right?
15 divide 5.
50, yeah, there you go. 15, and I kind of gave it away there for you. 15 divided by 3, that'll get you back to 5. So it looks like this might be the best strategy for you. If you take all the miles that you want to go to, which in your case is 75, and you divide it by, you're only going to go 3 miles a day. If you can work that part out, you probably figure out how many days it's going to take. Let's do that part together. Ready?
Okay.
How many times does 3 go into 7?
4.
Oh, a little bit less. We don't want to go over too far. How many times does 3 go into 7?
2.
3, that's it. We got 2 of them, and 3 times 2 is 6, so we'll subtract that out. Oh, here comes a real familiar number. We just got through doing that. How many times does 3 go into 15?
5.
There you go. That's exactly it. And we don't even have a remainder, which is super nice. So we don't have to worry about making a fraction like in the last one. But that's it. 25 days will get you to 75 miles. Is that a full month?
Yes.
Even in the shortest month, we have 28 days, right? So we're almost there.
Yeah, so we're almost there.
Yeah, we're almost there. That's a lot of walking, though. Interesting. All right, so 25 days is what we ended up with. Great question. Thanks for calling.
Nicely done, Brian. Congratulations on that. And do remember, we have phone tutors available until 5:30. For that effort, we will also be sending you to Cubby's. Get yourself pizza at Cubby's Chicago-style pizza. We'll be back with more right after this. Today we're at Orangewood Elementary School, and today we're here to at Orangewood Elementary, and we're with 4th grader Arian. How are you?
Good.
All right, you ready to do some math problems?
Yeah.
All right, let's take a look over here. You eat pizza? Yeah? What kind of pizza you eat?
Pepperoni.
Pepperoni? That's good stuff, isn't it? Ooh, I like pepperoni too. So, let's say that we have 4 pizzas. All right, and each one of those pizzas has 8 slices. And how many people do you usually have pizza with?
8.
8 people? Wow. All right. Well, you know what? It's a good thing that all of you ate 21 slices.
Whoa.
Whoa is correct.
I'm going to be full.
Well, yeah, I imagine you would be after 21. But we're going to have to figure out how many slices are left over. All right? So, first of all, we need to probably figure out how many slices there are. So how are we going to do that?
Multiply 8. Multiply 4. So
All right. Well, grab the marker and go ahead and get to work. All right, so what's 32?
32 slices. Yeah.
32 slices. And are they all pepperoni?
Yeah.
Okay,
Here,
so
I'll
you're right.
label it.
There you go, perfect. See, if you label it, it's easier for me to understand. All right? And you ate how many?
I ate 21.
Okay, so now what do we do?
we subtract 21. Well, you subtract 32 and 21.
So do I subtract 32 from 21, or do I subtract 21 from 32?
21 from 32.
Very good. So let's go ahead and try that. So you have 11 slices left over? Okay. If we have 11 slices left over, do I have a whole pizza left over?
No. Well, yeah.
Which is it, no or yeah?
Yeah.
Okay, so how do you know? Because are you like telling me or guessing, or what are you doing?
Because if there's 4 pizzas and 4, yeah, minus 4, then that's 11. Wait, 4, 5, 6, 7, 8, 9, 10, 11. So that's 7. So, and then you have 7 pizzas.
Okay. That's if we had whole pizzas.
Yeah.
All right, so look, we have 11 slices. How many slices are in one pizza?
8.
So if I have 11 and I take away 8 slices, that'll be a whole pizza? So let's say I take away 8 slices, that would be a whole pizza, right?
Yeah.
And how many slices would then be left over? There you go. So you actually have a whole pizza left, don't you? So in case you get hungry later on, right?
Like, or you could have it for breakfast.
Oh, there you go. Pepperoni pizza for breakfast, huh? Arian, nice work.
Of course, they see the rock tower when they come in and they get anxious and they want to get on that right away, but we have to make sure that they can follow the rules. We have to be able to trust them. They need to be able to trust themselves. Today we're seeing an at-risk youth group come out and just explore the Condor Challenge, kind of see how they can be successful in many different ways.
Get the ball, bro. Get the ball.
We're focusing on communication, leadership, trust, and then we also have introduced consequences. Whether or not they're successful just depends on how well they work together.
What I hope for them is just to learn some team building skills. They don't have any right now.
Like this, look.
This is definitely going to help them and just develop socially and just learn how to trust one another.
There, now you're good. Walk across now. You're good. It's not gonna break.
They need this mentally, emotionally. I think it'll definitely plant a seed for their future.
Good job, guys. Nice reach. The whole point is for them to walk away feeling successful and confident, and hopefully they can achieve anything else outside of here by using those same strategies.
There you go. Nice, man. Good work. All right. It was scary, honestly, nerve-wracking. Just concentrate on the log in front of you, not looking down.
Pull it all the way up and over your shoulders and set it over your shoulders, and I will help you.
Watch the rope, you guys. Make sure you're not touching the ground.
Safety is always number one here. With our 5-finger contract, it's our smallest little pinky finger, but it really represents a very important part of the Condor Challenge. But really what it comes down to is just evaluating each individual participant and not putting them in a situation that they wouldn't be able to overcome.
Yeah, nice work.
I've seen a few students take leadership roles, work together and push one another. They're not putting each other down like they would back at home. Here, they're building each other up and encouraging one another, which is spectacular.
All right, you never know what you'll find out at COM. That, as well as the holiday lights, as well as all the animals out there on a regular basis. We do have phone tutors available until 5:30. Dylan from Stockdale is working. We need to get busy on your homework.
Yes.
Back to the board, young man. Here we go.
Let's do it.
So now we have 4 students. So you can go ahead and put that number 4 up there if you think you're going to need it. And they have a 30 square foot wall.
Whoa.
How many square feet of the wall will be painted by each of the students? So you have 30 square feet.
Wow, I messed up.
That's all right. So 30 square feet, and they're gonna paint it, huh?
And there are 4 of them.
So what do you want to do with this?
Tape diagram.
Ah, tape diagram.
Here, I might need some more.
Nice small one. What are you gonna draw here? Are you drawing 30 pieces or are you drawing 4 pieces?
30.
Whoa.
They're going to be thin there.
Yeah, we're gonna be a little bit thin. I think we might need to go a little bit bigger there.
Maybe.
Man, that's a whole bunch of them. Well, how about this? We certainly can draw a tape diagram. Maybe we can do a little bit of that tape diagram after you tell me about the math. What is the ultimate math we're going to do here?
Mostly tape diagrams.
Okay, but tell me about the math. Is it addition, subtraction, multiplication, division?
Oh, it could be anything.
It could be anything, that's right. But most tape diagrams, at least according to our last one, what do we do with that problem?
Add and subtracting fractions.
Mm-hmm. And what did you have when you had a remainder in that part?
Turn it into a fraction.
Yeah, we did turn it into a fraction. And which operation is a fraction?
Dang it, what was it?
Well, it's not addition, right? You're not going to add those numbers. So if you have like 8 over 2, and you want to change this,
Simplification.
Right? You simplify, right? But what do you do when you simplify this one? 8 over 2 is what?
It's a mixed number.
It is, yeah, that's right. So what do you do to make this into a whole number? You told me earlier, right? It's this top number. Add, subtract, multiply, divide. What do you think? Which one?
Divide.
It is divide, yeah, that's it. And the way that I remember that is because division has a big line in there, and so does this one. Kind of like 2 dots right there, right? So the same thing is kind of happening on this problem here. At least we can think about the math a little bit. We have 30 square feet, right? And we have to divide that amongst 4 different people. Can we do the math part first, and then we can maybe draw a little picture that goes with it? Otherwise, we'll be drawing lots of lines. I like this tape diagram, but it could take a while. Just right underneath, we can even make the tape diagram when we get done if you want. Okay. Just right underneath here, can you do that? Your 30 divided by 4? There you go. Good. Okay, so let's see what happens here. I'm going to give you a little more room and see what happens when you divide 30 by 4. Oh, I see what you did there. Tell me a little bit about what number is this? Is this a 7?
7.
Okay. Does 4 go into 3 7 times? It doesn't, huh?
It can't go into it.
Yeah, it doesn't. So that really would be a 0, right? 4 goes into 37 times, right? So when that happens, just make sure you put your 7 over top of the 30 and not just the 3, okay? I like your 7 there. Good. We have a little bit left over. Let's see if you remember from the last problem. What are you going to do with that remainder?
Turn it into a fraction.
Okay, let's do it. You got 7, and then the remainder goes on top.
2/4.
That's it. Can you simplify that fraction? Yeah, 7.5. So back to our tape diagram. There's going to be 4 separate groups, and how many slices or how many pieces are going to be in each group?
7.5.
7.5, right? So let's say that is 7, right? And we're going to have a little thing in the middle here, and we're going to have a half. There you go, good. And let's say that we have another 7 right here. And there's your half, good. And let's say that we have another 7 right here. And we'll go ahead and divide it up in half. And another 7 right here.
And this is their half.
There it is, right? So certainly you could draw out all those lines, and that's not a good time, but it would be a pretty long tape diagram, right?
Yeah.
The great thing about a tape diagram is knowing that it's a division problem, and you have the division to back up your work that's right here. So you can show, someone says, really, I can't quite see how those lines are the 7.5 in each group. They're so skinny. Say, well, look at the math. I promise you it actually works. So I like that problem a lot. Did we answer the question, Mike?
Indeed we did. And right now we're going to continue moving on. We're going to go out and about, finish up with Marylou.
Today we are at the Public Works Traffic Division, and I am again here with Ed Murphy, Civil Engineer 3.
Whoa.
And we were talking about, we were in the control center, and we could see all the traffic lights that are going on and intersections that have cameras, and see all that. From that, you can kind of take information about determining things that's going on in the street.
Yes,
right?
such as the speed of cars that are driving on there, getting a typical speed profile of the cars that are driving on a typical roadway. And I could show you how we do that right over here. First off, we have these, probably seen them out on the side of the road, or this hose going across the road connected to this, we use it for counting cars, but we also use it for determining speed, which I'll show you here in a minute. And these are laid out, they take air pressure in the end, and every time a car drives over it, sends the information into this box, and then we download it into the computer when we bring it back here in the office.
See, whenever I drive over those, I'm thinking, oh, I'm going to be in trouble here.
No, you're not in trouble. We're just trying to gather data to get an idea of what's going on out there so we could help better serve you and every other driver and pedestrian and bicycle rider out there in the city. So here's a little stick figure sketch of two intersections in the roadway between them. And here's the little box that we would lay. We'd chain it to a tree or a sign or something like that. Please don't steal our boxes or our hoses. And lay the hoses out across the roadway at, we're typically 10 feet apart. Now, where does the math come in? We're trying to figure out the speed. We know the distance between the two hoses, and as the car drives over it, it hits the first hose and then hits the second hose, and there's an amount of time difference between it. We know the difference of the distance over the distance of time, and the change in distance over time is the speed. And that's what we get. So let's say we have 3 cars that drive over this, and the first car drives over it, and by the time it hits the first wire, the second one, the time was 0.273 seconds. That seems pretty fast, and it is. It's almost like swimming in the Olympics. It goes down to that, because if the cars are driving like 30 miles an hour or 50 miles an hour, it's, you know, boom, boom. You feel it as you go over the hoses. So we know the distance between them is 10 feet, and the time it takes to go through it is 0.273 seconds, crunches out to 36.67 feet per second. But in units that we use in traffic engineering is miles per hour, at least in the United States. That's how we typically do speed. So we want to convert that from feet per second into miles per hour. So for the distance, 1 mile is 5280 feet, and then there's 3,600 seconds in 1 hour. We multiply that through, the feet cancel out, the seconds cancel out, we end up with miles per hour, and we get 24.78, which is about 25 miles per hour. Same thing with the car number 2. We, let's say they drove over it at 0.170 seconds. That crunches through into 40 miles per hour. And whatever the time is between the two hoses, that's how we determine the speed. And then we can add those up, all the speeds up, and divide it by, to get the mean or the average speed, add all the speeds up, and then divide it by the number of cars in our sample. For this case, we only have 3 cars. We add all 3 of the speeds up, divide by 3. The average speed is 40 miles per hour.
So you know that maybe that an average speed to set for that street would be possibly 40 miles per hour.
Yeah, we use a different, for setting the speed limit, we use a formula similar to the mean. It's called the 85th percentile. It's a little more complicated. I don't think we have the time to get into it now. But that would be 85% of the vehicles surveyed are traveling at that set speed or less.
And you kind of have something...
Sure. In this case, we don't put the hoses out when we do this today. We use a radar gun. And unlike police out there trying to give you a ticket, we're not trying to do that. I'm just trying to get, like I said, we hide in the bushes so you don't even know we're doing it. And we take a sample. In this case, we took 105 cars, typically 100 because it keeps it an even number, but let's complicate things right now, right? So 85% of those cars is about, what did we say? 81, it was like, it's about 89 or something like that. Sorry. Yeah, 89 cars. So here we see, as we add them up from the bottom up, like I said, it's 85% or lower. 1 car was going 40 miles an hour. We got 2 cars going 42 miles an hour. We keep adding them up, and somewhere 89 is somewhere between here, between 54 and 52. So the 85th percentile speed is about 53 miles per hour. to set the speed limit, we always round up, and that would make the speed limit. This is the computerized program that does all the crunching through, does a few more extra calculations, and we set the speed limit at 55 miles per hour.
Now, like you said, it's not you guys who are really setting it, it's the public, right?
Drivers, yeah. Like I said, we want somebody, we take like the first car of a platoon or just went the comfortable speed of them driving on the roadway. And of course, laws come into play. Near a school zone, it's 25 miles per hour. In a residential area, maximum speed is 25 miles per hour. You know, there's in maximum speed in California, I think on freeways is 60. You know, there's other set laws that we have to observe, but local roadways, arterials, collectors, could be anywhere from 25 miles per hour to 55 typically on the faster arterials. Yeah.
Now, what schooling did you need for this profession?
I am a civil engineer. I got my bachelor's degree in civil engineering, and that was years ago. Lots of math. I'd also like to say, in addition to math, also just writing skills and social sciences. I mean, you need to know the technical part right here, but then you also need to communicate it to your boss and to other people in the public and relate to others. So, you know, a lot of technical writing classes and things, don't neglect those, but certainly paying attention, a lot of attention to the math. And your efforts are not in vain. You are spending quality time working these problems. Because later in life, when I took physics, I remember in college, it was, then I really saw how the math made the physics so much easier. And it really made sense, and it really came to life. And it really, yeah, it was really exciting.
Cross-curricular is what it is.
It is, but it was a tool, it was a language that helped explain what was going on. And nowadays, I look up a lot of things in a book, a formula in a book, but I have that background training, and my mind's been trained on how to think critically, you think mathematically, and apply that to what we're doing here today. So it may seem a lot of simple math we've done, but I put in the time, trust me.
There's a lot.
But very enjoyable, a lot of fun. Anyone can do it if you work hard enough. It took me a while. I'm not the smartest guy in the book, but absolutely, and it's a lot of fun. This has been a good choice of vocation.
Thank you again, Ed, for letting us come today
You
to
are welcome.
visit the Public Works Traffic Division.
Yes.
And all the new technology and everything going on here has been absolutely amazing. And being able to see all the cars and the intersections and how your maps work with all of your signals. Truly amazing. And here's a little something
thank you.
to thank
Cool.
thank you for letting us visit today. And so we are going to head back to the studio.
Thanks for that, Marylou. Another supporter of Do the Math. A lot of things behind the scenes right there with traffic and what's going on.
Yeah.
Hey, we do have phone tutors available until 5:30. We have Dylan in studio, and we're going to continue with the next problem that you're working on, because while we were taking that little break, we had you finish up that other side, all right? So head on over to the board, and we'll work on problem number 2. Many parts to every problem, so this is nice. Problem number 2. Craig bought a 3-foot-long baguette, so 3 feet long, and made 4 equally sized sandwiches with it. So, part A, what portion of the baguette was used for each one of those?
Wow. Any idea how we're going to do this one?
Tape diagram.
Oh, tape diagram. All right, I'm going to draw you a 3-foot baguette that's going to look a lot like a rectangle. Okay, so we'll say that this thing is 3 feet long. What do you want to do with that thing?
So
You want to divide it up into feet first?
Yeah.
Okay, so here we go. You told me I'm going to do one less. So that's 1 foot, and that's 1 foot, and that's 1 foot. 1, 1, and 1. All right, so now we got to split that into 4 equal parts. Whoa, what are you going to do with that?
So it's 3 feet long baguette. So it's either that way or
It's
the
either
other
that way or the other way, huh? Yeah, it's kind of hard to figure out. Well, here's the thing. Think about how this problem goes down, right? This is a 3-foot piece, and we're going to divide it
by 4.
into 4 pieces, right? Yeah. So do you want to switch those numbers around?
Yep.
Okay. So we'll see what the math looks like, and then we can maybe draw a picture that goes along with it. Okay?
And then it can't go into
It can't even go. So what are we going to do with that? Can you make this into some kind of thing? Maybe we were using fractions earlier, right?
Yeah.
Can you make this into a fraction?
Yeah.
What is that?
3/4.
Oh, 3/4. So the question said, what part of the whole entire piece of bread is each sandwich, right? I'm pretty sure you answered that, but we need to draw it.
Yeah.
Okay, so the first one's gonna be not so bad, right? You got 3/4. Go ahead and draw. What is 3/4 of 1? Where would that line up?
That'd be 3.
Now you just drew 3 whole pieces, right? We don't have that much. We gotta go backwards on that one. Let's see if we can take those away. We just want this piece right here, okay? What happens if I had 4 sections of that one? Can you fill in 3 of them? 1, 2, 3, right? And we have 4 sections of this one. Can you fill in 3 more? 1, 2, 3, good. And we have 4 sections of this one. 1, 2, 3, you have 4 sections. 1, 2, 3, good. So we've made 3 sandwiches. And how many pieces do we have left?
We have 3.
We got 3 pieces left, so we can make another sandwich. It's a total of 4, right? And each of them has
1.
3 sections, right? So 3/4 of a foot would be each individual sandwich. I think that answered that question. Do we have a second part to that one, Mike?
Well, you know what? We're going to stop on that right now. So come on over, Dylan, because you have done some outstanding work right there.
I like what you did.
And I wanted to ask you, so in class, it seems like you guys are doing a lot with the tape diagrams right now. So is this the first time you're doing problems like this, or have you used something besides tape diagrams before?
We've been only doing tape diagrams. My teacher really wants us to learn tape diagrams.
All right. And how long have you been doing these now?
3 weeks.
So a couple of weeks. So you're feeling pretty comfortable with the tape diagram?
Yeah.
All right. And do you think there are some other ways to solve the problems?
I don't know. There probably are, but I probably don't know them.
Well, you know what? That's the beautiful thing about math, is because there are so many different ways that you can solve problems. And the good thing about the tape diagrams is that you have something visual that you can represent the problem with. So it makes a little sense when you look at it, and kind of logically you're looking at it going, yeah, that's reasonable. If I have this 3 feet, you know, of whatever it is, and I need to cut it into 4 equal pieces, what will that be? So nice work on that today, and I'm sure that you helped out a lot of other students that were kind of struggling with those same kinds of problems, but using a tape diagram probably helped them out.
Yeah.
I need you to help me out now, all right? Because every time a student phones in to do the math, their name gets entered into a drawing, and we give them 2 tickets to any CSCB athletic event of their choice. So I need you to reach in there and pull out one of the names from the students that phoned in today and see who our winner is.
Audrey Bill Williams.
All right, there we go. So congratulations to Audrey, phoned in with one of the math problems. And Audrey from Bill L. Williams, 6th grade student, if I do recall, will be going to a CSCB athletic event of her choice. Do remember, we have phone tutors available until 5:30 this afternoon, as we do most Tuesdays and Wednesdays throughout the regular school year. And until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Southern California Gas Company, California Resources Corporation, Kern Schools Federal Credit Union, Panama Buena Vista Union School District, Bakersfield City School District, and the San Luis Obispo County Office of Education, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.